Hello again, Galen Pickett, Cal State Long Beach. This is Physics 151. We're now moving into Chapter 3. And you should be reading the entire chapter on your own. The homework you're doing takes from everything that's in Chapter 3. But I did want to talk about the form of the gravitational force near the Earth's surface, Section 3.3 here. So that's what this little video clip is going to be about. So Section 3.3, gravity, universal and near the surface of the Earth. So here we have an object of mass capital M, an object of mass little m, and they're a distance little d apart. Newton's universal gravitational force law says this force, that this object will have a force on it in magnitude capital F that points towards the other object. There'll be a force in this direction. I'll call it little f. So there's an attractive force between these two objects. F in magnitude is equal to the universal gravitational constant, the mass of the big object, mass of the little object, divided by the distance between them squared. And the direction is given by this little geometric construction here. You figure out what's the vector that takes you from big M to little m, and you divide it by its length. That tells you what is the unit vector. If I ask for the little f, what is its force? Well, it's exactly the same expression, but I have to change the order in which the two masses occur. So it's universal gravitational constant. First, I take my own mass, little m, and then the mass of the other object, divided by d squared, and I see there's a remarkable property here. The forces on the two objects are exactly the same. And whether you believe that or not, the forces are exactly the same. This commutation operator, this multiplication operator between these two objects, it doesn't matter which order you put them. So the forces on the two objects are the same, but we know that you need to know the mass of the object to figure out how the force tells the momentum how to change. And this is the universal gravitational force law. All gravity, as long as we're not talking about something big enough to be a black hole, a neutron star, very strong gravity, as long as we're not talking about something that the quantum world is relevant for, this is how all gravity in the universe works. But we do have this statement that the force of gravity, this was from Galileo's experiment, for an object near the surface of the Earth is the mass of the object times this little g thing, and then if z is the direction it goes away from the Earth, so here's the z direction, the force on the object points downwards, and F sub g is as given there. How is it that these two things are the same? Well, let's take a look at, say, me. Oh, that's a terrible circle. Let's take a look at the Earth. So it's got a radius r, it's got a mass m sub e, and I am going to be standing here on the surface of the Earth. I'm the little m. And I want to know what is the force that of interaction. The Earth is interacting with me through this universal gravitational force. Now, the distance to use for the gravity law is not my distance from the ground, h. It is the distance to the center of the Earth, and for almost everything near the surface of the Earth, that distance is the radius of the Earth, 6,000 kilometers, 4,000 miles. So the force that's on me points towards the center of the Earth. Force on me points towards the center of the Earth, so I'll write that as minus r hat. It has got my mass, it's got the Earth's mass, it's got the radius of the Earth squared, and the universal gravitational constant. If I put all of this stuff that depends on the Earth, so I've got the mass of the Earth, this little g, and the r squared. The stuff that depends on me is my own mass and where am I standing on the Earth, and what is the direction that is locally down towards the center of the Earth. If I do that, I can rearrange this as minus m r hat times a bunch of things that depend just on the Earth. Universal gravitational constant, mass of the Earth, r squared. And this thing has got units of meters per second squared. This thing has got units of kilograms. Numerically, this thing is actually equal to this little g thing of 9.8 meters per second squared. So if I'm standing here, I've got a little force downwards in that has got a size of, say, if I've got a mass of 80 kilograms, that would be 800 newtons downwards. There has to be a force on the Earth upwards that has the same 800 newtons. But that 800 Newton force upward and my 800 Newton force downward, My 800 Newton force causes me to accelerate towards the ground with an acceleration of about 10 meters per second squared. For the Earth, it accelerates towards me much, much more slowly. That's why you don't feel the Earth moving when I'm jumping up and down, and you've got a problem exactly exploring this. You've got all the people on the Earth. So you've got 6 times 10 to the 9 people, all jumping upwards with some jumping speed from the surface of the Earth, and you're going to calculate what is the recoil velocity of the Earth because of that jump. That's one of your homework problems. It's one of the most sophisticated homework problems you've got this semester, and a social homework group is going to be has been assigned to it, a couple of them, and we'll take you through that.